Hello guys, this is CodeNCode and this is video editorial for the problem walk to remember taken from HackerEarth. So the problem is this is useless. Okay, the city in which Dilku lives is represented as an unweighted directed graph. So basically we have directed graph with no weighted edges with n nodes and m edges. A special walk in a graph starts at node u in a simple path that begins and ends at the same node u. Basically you should a node u will be called a special walk. Okay, a walk is special if you start from a certain node, take some path and end at the same node, then this walk would be called a special walk. A walk is basically series of nodes that you visit. So the walk which we are talking here, the special walk, is that kind of walk where you start on a certain node you visit certain see here, visit certain other nodes. You start from u, then visit some other nodes a1 a2 dash 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 ai, and then end your walk at u as well. So basically this should be a cycle, this should form a cycle. If so, then this walk is called a special walk. So basically what we have to do is, for every node u in the given graph, if there are like 5 nodes, so for each node 1 2 3 4 5, we have to tell whether it is possible for each node you have to tell whether you can start or there exists a special walk or not starting from that current node. So if I explain you with an example, so here you can see there are 5 nodes and 5 edges and an m. The graph would look something like this, right? So here you see you can start a walk on node 2 and you can end it at on node 2 as well. For example, you can go here, here and here. You are starting a walk on 2 and ending it on 2 as well. So that is why 2 for 2 we would print 1, because yes, there exists a special path, special walk, I guess, special walk starting from node 2. Similarly for node 3, starting from node 3 there exists a special walk. And how is that? You start from 3, go to 4, go to 2 and then come back to 3. Similarly for 4, for 2 3 4 there exists a special walk starting from these nodes. That is why for 2 3 and 4 we are printing 1. Then yes, a special walk starting from these nodes exists. For 1 and 5 we are printing 0, because for node 1 and 5 there doesn't exist any special walk that starts at 1 and end at 1. Similarly for 5. So basically a special walk, if you have a cycle, right? So or any node on that cycle, for any node on that cycle we will be printing 1, because if that is a part of a cycle, if that node is a part of a cycle, then what would happen? You can always start from that node and reach back that node. And that is why whenever you see a cycle, all of the nodes in that cycle, we are going to print 1 for them, because there exists a path, a special walk starting from that node and ending at that node as well. So the question simply asks you to find all of the cycles, and for each node in that cycle simply print 1, right? So this is the question. So we are going to solve this problem using Kosa-Raju's algorithm and strongly connected component. What we are going to do, you remember, for those guys who do not know strongly connected component or Kosa-Raju's algorithm, I have a complete playlist, basically a complete course, Graph Theory Part 1, in which I have explained strongly connected component along with Kosa-Raju's algorithm, as well as Tarzan's algorithm, by the way. So you remember in the Kosa-Raju's algorithm I told you that every strongly connected component with size greater than 2, any strongly connected component having greater than equals to 2, having nodes greater than equals to 2, is a part of a cycle. So what we are going to do, we are going to find every strongly connected component, and for each for a strongly connected component, if it contains more than or equal to 2 elements, then for all nodes in that strongly connected component will be marking 1. For example, for this graph there are 3 strongly connected component, 1 5 and this. See, so 1 forms a strongly connected component of size 1. So this cannot be a part of a cycle. Similarly, 5 forms a strongly connected component. Again, size of this strongly connected component is only 1, so it cannot be part of any cycle. Here this forms a strongly connected component of 3 nodes, which means since 3 is greater than equals to 2, hence there exists a cycle among these nodes. Basically all of these nodes are part of some cycle in this strongly connected component, and hence all of these nodes, for all of these nodes we are going to print 1, and that is basically all that we are going to do. So if you want to solve yourself, you can pause the video, do it yourself, because I'm going to show you the code. So first of all, you will be provided n and m, n the number of nodes, m the number of edges, and I'm running a loop from 1 to m, basically reading all of the edges. So reading a and b in the graph. In the adjacency list of a, I'm inserting b because this is the graph, and the edges from a to b, that is why in the graph I'm inserting b in the adjacency list of a. Now here this is the reverse graph. If you remember, Kosa-Raju's algorithm requires graph and the reverse graph as well. So this is reverse graph. So since the edge is from a to b, that is why in the adjacency list of b I'm inserting a, which is basically reverse edge. So this is the original graph and this is the reverse graph. After that, we are what we do, we calculate the order in which the second DFS has to run, this order. Again, this is all I have explained in the Kosa-Raju's algorithm. So what we do, we traverse the whole graph, here running a loop from 1 to n, we are traversing the whole graph. If ith node is not visited, then we are making DFS call to node 1, which is responsible for calculating our order. After that, what you do, first of all we need to reverse the order, and after that mark, since all of the nodes, while you are making DFS call to calculate order, all of the nodes have been visited. So again run a loop from 1 to n, mark them all unvisited, because Kosa-Raju's algorithm requires 2 different DFSs. One series of DFS is here, other series of DFS is here. One series of DFS to calculate the order in which you will traverse the reverse graph, and that is happening here. So for each node in the order, if the current node is not visited, then you make a DFS call to that node, and this is DFS1 as you can see, and this runs on reverse graph to calculate the strongly connected component. After that, before going there, we are clearing the SCC. What is SCC? SCC is vector, or basically a list. Here vector of int, this is basically a list, and before going for DFS1, which will calculate which will find out all of the nodes in the strongly connected component, in the same strongly connected component as this node. So I'm clearing the strongly connected component and then making DFS call. So after this DFS call, SCC will contain all of the nodes of current strongly connected component. After that, I'm simply updating the answer. Initially answer array is initialized with 0, all of the elements are initialized with 0. In the update, what I'm doing, if the current strongly connected component has size greater than equals to 1, then I'm updating, otherwise not. So how you are updating, for each node in the current strongly connected component, all you are doing is in the answer array, for that node you are marking 1, and finally printing the whole answer array. So most likely this should work. If we submit it, there should not be any TLE or wrong answer. Of course there should not be any TLE and wrong answer, because I have already tested this code. So yep, as you can see, AC. I'll be providing this code in the description of the video. If you have any doubt or query or suggestion for the next graph theory problem, you're more than welcome for that. So this was all for this lecture. Thank you guys for watching. Until the next video drops, keep coding. Thank you.